It's like with radio, with countdown. Okay. So welcome back to the section number 10 on PDE. I'm Felix Otto from the Max Planck Institute for Mathematics and the Sciences in Leipzig, Germany. It's a pleasure to introduce Mathieu Lewin. Mathieu is Directeur de Recherche, that means with CNRS at Paris Dauphine. He was awarded the prize of the European Math Society in 2012 and was holding, now is still holding an ERC consolidated grant. His expertise is, I would say, at the intersection of mathematical physics and the calculus of variations, which means the calculus of variations in high dimensions, and specific focus is on the fundamental challenges of many-body quantum systems and their effective behavior, revolving, for instance, around Hartree's approximation method, but he's also interested in crystallization and defects. And today he's going to speak about mean field limits for quantum systems and nonlinear Gibbs measures. Please, Mathieu, the floor is yours.
Thank you very much, Felix, for this very kind introduction. And of course, thanks to the panel and the program committee for giving me the opportunity to talk today. So as you said, Felix, I'm going to speak about mean field limits for quantum systems. I'm going to do a review of results I got in the past years, and in particular, insist a bit on some more recent results concerning nonlinear Gibbs measures. So in short, what's the problem? What we want to do is to compare these two equations, these two PDEs. Both describe n quantum particles. So the first PDE is this one. It's a linear PDE in very high dimension, in dimension d times n, where d is the space dimension and n is the number of quantum particles. So it's an eigenvalue equation. So the unknowns are, of course, psi and e. And here are three terms. So the first term is just the Laplacian. So that's the kinetic energy of my particles. The second term is the potential. So we are just putting some external potential in order to control our quantum system. And the third term are the interactions between our n particles. And that's why you sum here over pairs. I have added here a parameter lambda, which I will use to modulate the strength of the interactions. The second PDE I'm interested in is this one here, which is of nonlinear Schrödinger type. It's sometimes called the Gross-Pitaevsky, sometimes called Hartree. Here we call it Gross-Pitaevsky. It's a nonlinear equation in Rd, so n has completely disappeared in this equation. And it's a mean field equation in the sense that we make the assumption that the particles are IID, and we assume that they all share a common quantum state U. And then we get this equation with this effective potential here, which we call the mean field potential. And the form of this potential really follow from the law of large numbers. So our goal is to justify why the second equation is a good approximation to the first equation in some limit. And the limit is written here. It's going to be n to infinity and lambda of the order of 1 over n. So before I speak about this limit, maybe I should mention that if lambda is 0, or if you prefer, if w is 0, then the two equations are just essentially the same, even for finite n. So in the sense that if you consider here an eigenfunction of minus Laplace plus v, so you remove the nonlinear term, and then you can immediately build an eigenfunction of the sum here just by taking the tensor product u to the n. So if you like u of x1, u of x2, and so on, u of xn. This is an exact eigenfunction of this operator here without w, and E is just equal to n times the eigenvalue. So of course, the idea is that if lambda is very small, then psi must be close to a tensor product. However, it's not very interesting because in this case, you would just get a linear equation as an effective PDE. And here we want to look at the case where we get a non-linear equation. And for this, the regime I mentioned is very important. So why you want to take lambda of the order 1 over n? That's just because you want all the terms here to be of the same order, meaning n. And since here you have of the order of n squared terms, then you have to take lambda of order 1 over n. What's difficult is that in this limit, psi is not going to be close to a tensor product. It's going to be a little bit more subtle but I'm going to explain in the talk. So perhaps a question you want to ask is, why is it so that for this limit, the second equation is going to be an approximation of the first? Why is the mean field regime valid? And you should think that the reason is that it's a high density regime. So meaning the second equation is going to be a good approximation to the first whenever you have of the order of n particles in a bounded region of space. So high density, a lot of particles. This will in general depend, of course, on V and W. And why do you get some collective behavior at high density? Well, imagine that you walk in a crowd of people. So if the crowd is not very dense, then you will easily find your way through the crowd and you will be able to go wherever you like. But if the crowd is very dense, then you will just lose all your freedom and you will be just forced to follow the crowd motion. So you see that in the high density limit, typically some collective behavior can arise. So mean field limits have a very long history and they are used in many different situations. And they have also been studied a lot on the mathematical side. So both classical, quantum, stationary, or time dependent. So here I was discussing the quantum stationary problem. And the master of this problem is Elliott Lieb, who was awarded the Gauss Prize on Wednesday. So he proved the theorems of the sort I mentioned in the previous slide relating the two equations for many different systems. In this talk, I will explain a new method which we introduced with Nam from Munich and Nicolas Rougerie from Lyon, which is somehow more conceptual, more general, more abstract, and which allowed us to get a very general result covering all previous theorems. Our method is based on a non-commutative probabilistic tool, which is called the quantum de Finetti theorem. And it is somehow so robust that it allowed us to go further and then study nonlinear Gibbs measures. But before I start describing a little bit more what we can prove, let me make some comments about the physics. So this question is typically useful for modeling Bose-Einstein condensates. So let me remind you or tell you that at extremely low temperature, some gases made of some specific atoms like bosons are expected and are known to undergo some phase transition at very low temperature. And the phase transition is really an emergence of a collective behavior in the sense that all the particles start to behave the same and share a common wave function u, solving the Bose-Pitayevsky equation. Here on the left is a picture of an experiment made by Ketterle at MIT. So what they do is they make such a gas rotate very fast along some axis, and then they take a picture from the top. And what you see here is the density of particles. And you see these little dots here are just holes, so vortices actually, where there's no particle sitting, and they just sit on a triangular lattice. On the right is a numerical simulation from colleagues in Nancy about the Bose-Pitayevsky equation with an additional term for the rotation, and you see you get exactly the same. Let me mention as a side remark that proving that these vortices really crystallized on a triangular lattice is a very famous open conjecture, and it would actually follow if Marina Wiazowska could prove her theorem in dimension 2 instead of dimensions 8 and 24. I have to tell you that for Bose-Einstein condensate, it's not quite a mean field limit which is the most relevant. It's rather a dilute limit, but it's a little bit complicated. I'm not going to go into these details. Works in these directions are due to Lieb, Schrödinger, and Ingwersen. And finally, concerning nonlinear Gibbs measures, so in this context of the Bose-Einstein condensation, they are going to describe really the formation of the condensate, so what's happening exactly at the critical temperature. And this is related to what Hugo Duminil-Copin told us on Wednesday about the Gaussian free field appearing in dimension 4 at the phase transition. Here it's somehow the same, except that we don't get the Gaussian free field, we'll get some interacting field. Okay, so let me now start with the math and describe a little bit what we have done. So I'm going to denote by Hn lambda, the n particle Hamiltonian, which has this kinetic potential and interaction. And then I will introduce the Gauss-Pitayevsky energy here, which is the one of which the stationary points solve the Gauss-Pitayevsky equation. In this talk, I will mainly look at minima, ground state. So I will minimize the energy, I will minimize the quadratic form of H, and then get some specific solutions. So I'm calling E of n lambda the first eigenvalue, or the bottom of the spectrum of Hn lambda, and I'm calling little e gp the infimum of the Gauss-Pitayevsky energy. And then the first result is a convergence just at the level of the energy. Let's start with a simpler problem of E of n lambda divided by n towards the Gauss-Pitayevsky energy. We could prove this theorem in two cases. So either the confined case where the potential V goes to infinity at infinity, and is otherwise very general in some LP space, and where P is just the usual P's which allow to control these two terms with a gradient using a Sobolev inequality, or the unconfined, or rather I should say the locally confined case, where V and W both go to 0 at infinity. I will always look at these two cases. And of course, the confined case is easier because you can't have any compactness problem, but the unconfined case is more complicated because you can have some lack of compactness at infinity. So this was for the energy. So now let me explain a little bit the idea of the proof. So first, as I said, there are many similar results in the literature for particular models, but here we get a general result working for all V and all W, essentially. So, of course, if you want to prove this theorem, there's an upper bound and there's a lower bound, and the upper bound is actually very easy. So what you do, you just take the exact tensor product. So you make the assumption that the particles are IID, if you like, and you compute the energy. What you get is n times kinetic plus potential energy, and then you get n minus 1 over 2 due to the number of pairs times lambda times the interaction energy. So you see that when lambda is exactly 1 over n minus 1, then there is an exact inequality that the capital E is less than n times the small e. And of course, when lambda is just of order 1 over n, then you can estimate the error and you easily get the upper bound. So the lower bound is, of course, more complicated, but it's easy if W is positive type. So namely, if W has positive Fourier transform. So in this case, you can use the following trick. You rewrite the double sum. So first, what you do is you add the missing diagonal terms. So here they are. That's the n over 2 times W of 0. And then you add a function eta, an arbitrary function eta, and you write this double integral with the sum of the delta at xj. Okay, and then you've inserted two terms. You've inserted this sum here as well as this constant there. And the whole point is that the first term is non-negative if W has a positive Fourier transform, so you can just remove it for a lower bound. So what you have done here is to estimate a two-particle term in terms of a one-particle term. In a sense, you've replaced your interaction by an external potential. And as I explained, when there's just an external potential and no interaction, then the comparison between the two models is easy. So then if you, in the end, optimize over eta, you will easily get the lower bound. This we usually call the Onsager argument. It's due to Onsager in 39, but I also would like to emphasize that this is the way that Kohn and Kumar get their linear programming bounds, which were mentioned by Wiazowski on Wednesday. So of course, if W is general, then the proof doesn't work. One has to do something else. And in our paper, we have a proof which I'm not going to discuss. And then in the proceedings, I have written a proof following Lieb and Yao, which is rather elementary. Okay, so this was only about the minimum. So now I have to discuss the convergence at the level of states and equations, if you like. Okay, so as I told you, it's going to be wrong that psi will be close to a tensor product. So the particles will not be IID exactly. but they will kind of be IID in average if we only look at some special events. Okay, and it's the same in classical statistical mechanics. So here what we have to do is to introduce correlation functions, and in quantum mechanics, correlation functions are replaced by what we call density matrices. The density matrix is not really a matrix, it's an operator, but we use this word because it's coming from physics. So I'm giving here the definition of the K particle density matrix, which is the following. So I take psi, and I use the fact that now I have two psi's. I don't have a probability, I really have a projection in a way. So I can put two variables, x and y, in x in Rd to the K. And then I integrate the n minus k remaining particles. So this defines me a function, and I see this as the kernel of an operator gamma k. And then I put the correct combinatorial factor in front. So this operator has a huge trace. So it has a trace n factorial over n minus k factorial, which behaves like n to the k. And then a norm which is less than the same number. However, in a usual large system, you should imagine that although the trace is big, the norm is usually order 1, just because the system is growing horizontally. But if you compute gamma k for an exact tensor product, so when the particles are IID, then you just get a rank 1 operator, obviously, which is n factorial over n minus k factorial, and then this notation, which means the rank 1 orthogonal projection on u to the k. Okay, so you see that the IID character can be detected at the level of the density matrices when there is an eigenvalue of order n to the power k. And so the main theorem is the following. So we take any sequence psi n, and we assume that psi n, it doesn't have to be an exact solution of Schrödinger's equation, it doesn't have to be an exact ground state. So we assume it just provides the energy to leading order. Okay, so the energy is of order n, as I told you. So I assume that it's E plus a little O of n. And then the theorem is that there exists a probability measure mu, which concentrates on the set of minimizers for the Gauss-Pitayevsky energy. And so that if I divide by n to the k, then the gamma k's, they all converge to U tensor k averaged against mu. And the convergence is strong in trace norm in case you work in the confined case, and otherwise it's a weak convergence if you work only in the locally confined case. And then you don't quite get the minimizers because they might not exist, but you get a measure which concentrates on the set of weak limits of minimizing sequences. Okay, so the spirit is that in the end, it's not quite that the linear Schrödinger equation converges to the nonlinear Gauss-Pitayevsky equation, but what you get is a measure, a probability measure, living or supported on solutions of that equation, and more precisely, not any solution, but the solutions which minimize the Gauss-Pitayevsky problem. So the proof of this theorem is not so difficult in the confined case. It follows quite easily from the quantum de Finetti theorem, which I will present next. And it was actually quite difficult for us in the unconfined case. So we really had to marry quantum de Finetti with many-body localization techniques and tools from the calculus of variation. So if you like, we had to do some concentration compactness on these systems of a growing number of particles and try to see what the particles are doing. So that's what we proved in 2014. So what is quantum de Finetti? So in 1956, in a famous paper, Penrose and Onsager, they predicted that the only way to have an eigenvalue of gamma k of order n to the k is by having some kind of condensate, so U to the tensor k. This was not really formulated mathematically, and then we noticed that this is true. It follows from the quantum de Finetti theorem, which goes as follows. So it's a general theorem which applies to any sequence psi n. It doesn't have to be a ground state, doesn't have to solve any equation. So you take any sequence psi n of symmetric functions on Rd to the n, and then you look at the density matrices. You divide by n to the k, you get a bounded sequence in the trace class, and after extraction, maybe you can always assume that this converges to some limit gamma k, weakly star in the trace class. The theorem says that these limits, they can't be anything, they have to come from a probability measure on the unit ball of L2, and then you get an average of U tensor k. Okay, so the theorem is telling you that the only thing that can arise at the scale n to the k in the density matrices is due to IID particles, and then you get a probability measures over all possible IID systems. And the convergence is strong if and only if mu lives on the unit sphere. Okay, so you should think that this is a non-commutative version of the Finetti and Hewitt-Savage, which has already been used several times in the study of mean-field limits. But it's a weak version of that theorem. Okay, so even in the classical case, I have not seen explicitly written the case of weak convergence, which we did here in the quantum case. It works the same in the classical case. And the strong version, so the one in trace norm, was from the end of the 60s and the 70s. In finite dimension, this theorem is very important in quantum information theory. And I have to also tell you that while we proved this theorem in 2014, there was a similar theorem, although stated differently, by Amari and Neer, which had been proved a few years before using semi-classical analysis in infinite dimension. Okay, so the summary is that we get a measure, a probability measure, which lives on the set of solutions to our nonlinear equation. But this doesn't tell us what psi is doing. Remember, we started with psi, so what is psi doing? In general, it's very hard to know what psi is doing, but we can go further, and that's what we did with Nam, Serfati, and Solovay in 2015. We can go further if we put more assumptions. So let me assume that the system is confined now, and let me also assume that the Gross-Pitaevsky energy has a unique and non-degenerate minimizer, modulo phase, of course. Then we can go further in the sense that we can expand the energy to the next order, which is going to be of order 1. Okay, and we can even do that for all the eigenvalues. So far I was only discussing the first eigenvalue, the minimizer, the ground state, but we can do it for any eigenvalue. And they all behave the same to leading order, but then to the next order, to the order O of 1, we start seeing the difference. And more precisely, we get an effective operator which tells us what the eigenvalues are doing, which is called the Bogoliubov Hamiltonian. It's a quite complicated operator, which I'm not going to define here, but you can read the details if you are interested. So it's an operator on Fock space, which is the direct sum of the symmetric tensor product of the tangent plane at U0, okay, meaning just the U0 perp. And this Bogoliubov Hamiltonian is just a second quantization of the equation of our mean field Gross-Pitaevsky energy. Anyway, so that's a complicated Hamiltonian, but this Hamiltonian tells you exactly what psi is doing, and it's the following, that psi will not be a U0 tensor n, but it could also have a U0 tensor n minus 1 and another function, and U0 tensor n minus 2 and another function. So if you like, we can start with U0 tensor n, and then we can excite finitely many of the particles without changing the leading order. Okay, and the theorem says that the excitations, the phi n, they will, if I put them all in the same sequence, then they will solve a linear equation with this Bogoliubov Hamiltonian. So this is the exact behavior of psi n. You see, it's not exactly a IID sequence, but almost, right? Because only a few particles are excited. And I have to tell you that there were previous works by Liv and Solovay, as well as Schrödinger on this problem. And in the next years, there have been lots and lots of works on deriving Bogoliubov theory. And Jan-Philipp Solovay is going to talk about it next week at the ICA. Okay. So that's the end of the first part of my talk. Now, I would like to speak about nonlinear Gibbs measures. So that's a new line of research which we started right after looking at minimizers. And if I summarize the situation once more, just to explain what we wanted to do, it's the following. So remember that we do not quite get a solution of the Bose-Pitayevsky equation. We really get a probability measure over ground states of a Bose-Pitayevsky problem. So a natural question is whether we can get other kinds of measures, not only measures concentrated on ground states. And of course, the natural measures are Gibbs measures. So what is a Gibbs measure? It's just exponential minus the energy. Okay, e to the minus d du. So of course, the difficulty is that what I've written here is completely formal. It doesn't make any sense because there's no du for functions. There's no Lebesgue measure in infinite dimension. Okay. Nevertheless, it's known, and I will remind you how it works, how to define this measure. And so what we wanted to do was to derive this measure from quantum mechanics, from our Hamiltonian Hn lambda, the same way that we derived it starting, in the case of minimizers. So it turned out that in one dimension, it was doable. We managed to do it in a year or so, but 2D and 3D are very hard, and it took us many years to complete this program, and and finally we managed to solve it in a paper in Invenciones, which is more than 130 pages. So it was quite a hard problem, and I'm going to describe what we did now. Okay, so the main difficulty is that these measures are very singular objects. So first, the energy, so I wrote e to the minus e, but the energy is always going to be infinite on the support of the measure. Even the mass is often going to be infinite. But worse than that, in dimension 2 and higher, then mu concentrates on singular distributions and not on functions, which creates huge problems in order to just define our energy, the interaction, and so on, and therefore requires renormalization. So we will have to renormalize something, and of course that will create problem on our quantum Hamiltonian, because we will have to understand how renormalization automatically come in this problem. Okay. So I have to tell you that before we started with n particles, and lambda was 1 over n, and then we ended up in the confined case with functions which were normalized in L2. And it's not so nice to look at functions at such measures restricted to spheres. So in order to simplify the setting, I'm going to look at the measure for U everywhere in space. So I'm not going to fix the mass of U anymore. But then I still want to control the average mass of U. So I'm introducing a new parameter kappa, which physically plays the role of chemical potential. Okay, so I'm replacing the energy by E plus kappa times the mass. And if I think in terms of the dynamics, then I'm just playing with two conserved quantities. One is the energy and the other one is the mass. Such measures have played a very important role in several areas of mathematics. So they've been studied in a groundbreaking work by Bourgain starting from the 90s. And that was about deterministic nonlinear equations with rough initial data. Okay, so these measures play a big role. They have also appeared in the case of stochastic PDEs, and they are used there to construct solutions of these rough equations. The idea is that they naturally arise as the long time asymptote of the flow. But otherwise, these measures, they were constructed way back in the 70s in the framework of constructive quantum field theory, in the Euclidean framework, by Nelson and Klim Jaffe and others. So we know everything about these measures. The question is really to understand how they arise from quantum mechanics. So what we will do in order to, I will first remind you how the measures are defined. And what we will do is to split the energy into the quadratic part and the nonlinear quartic part, okay? And then we will define the measure. We will put aside the quartic part and define the measure as an absolutely continuous measure with respect to the quadratic part, which is a Gaussian measure. So first, I will tell you how to define the Gaussian measure. So the measure we want to define is e to the minus the quadratic form, which has minus Laplace plus v plus kappa. Okay, this parameter we introduced, du. And the definition is kind of easy. So what we do, so we will assume that v is a confining potential, so that there is only discrete spectrum. And then we look at eigenvalues of minus Laplace plus v, as well as eigenfunctions. And we define this measure as this tensor product of Gaussians in each of the spectral subspaces. Okay? So for this to make sense, it's obvious that we need that lambda 1 plus kappa is strictly positive. So we have to take kappa strictly bigger than minus lambda 1. Okay? And then I have to remind you that when I write this tensor product here, so what I mean is I have a measure whose cylindrical projections onto any finite subspace of spanned by such eigenfunctions is exactly the tensor product. So that's the usual way of defining Gaussian measures in infinite dimension. What do we know about these measures? Well, so we know several things. So in order to be a little bit more precise, I will assume that V grows exactly like x to the power s for some positive s. So we know that the kinetic energy is always infinite mu zero almost surely. We know that the potential energy is always infinite mu zero almost surely, as I told you. That's because we are in infinite dimension. And then, depending on the dimension, the support of the measure is less singular or more singular. So in dimension 1, we know that the measure is really supported on functions. Actually, they are h1 half minus epsilon log. Okay? Meaning that locally there are perfectly nice functions in L2 or even a little bit more, mu zero almost short. This doesn't say that the mass is finite, right? Because you could have some decay problem, but it's known that the mass is finite if and only if S is strictly larger than 2. In higher dimensions, it's way more complicated because mu zero concentrates on distributions of negative regularity, meaning that everywhere U is going to be singular. It's not going to be a function. In particular, the mass is infinite, of course. However, if you stay below 4, so the critical dimension is 4, so in dimensions 1, 2, and 3, then there is a natural way, a simple way of renormalizing the mass. And the simple way is the following. So what you do is you project your singular distributions over the span of the J first eigenfunctions, and then you subtract the average against your measure mu zero. Okay, so you center your variable, if you like. And then the theorem says that this actually has a limit, which is a perfectly nice function. It's in L2 of the measure. And more precisely, if you compute the L2 norm of this renormalized mass, then you will find the trace of 1 over minus Laplace plus V plus kappa, so your kappa is missing, to the square. And then this constraint on S is exactly here to be able to have a finite Hilbert-Schmidt. Okay, so there's a natural way to renormalize the mass in dimensions 1 to 3 is if S is large enough, and this is called Wick renormalization. So how do we define the renormalized, now the nonlinear Gibbs measure? So we have to add this quartic term. In one dimension, it's pretty easy. Okay, so because of the properties of the Gaussian measure, then you know that the interaction energy is finite, mu zero almost surely, and it's actually in L1 if you put good conditions on W. I'm going to assume either that W is positive or a positive Fourier transform so that this has a sign. And then it's very easy to see that mu is well defined. In dimensions 1, 2, and 3, we have to do something else. We have to renormalize the interaction. But the thing is that the same Wick renormalization works, meaning you take, so the U of x squared, you first project in, then you remove the average. So you center your variable. And then you take the limit, and one can show this exists in dimensions 1, 2, 3. However, here it's important to assume that W is positive definite because now this has no sign. So if you want the integral to be positive, then you put this assumption. Okay, so these are the two objects we want to get. In one dimension, we want to get this e to the minus I times the Gaussian. And in 2 dimensions and 3 dimensions, we want to get this renormalized measure. So now there will be 2 theorems. The first will be about 1D and the next one about 2 and 3D. So here is the one-dimensional theorem. So as I told you, we are not fixing the number of particles here. So I have to average over n in order to get a measure living over the whole space. Okay, so there will be no fixed mass. And the way to do the average is well known in statistical mechanics. So first you consider e to the minus beta h. So that's the usual Gibbs, quantum Gibbs operator, okay? Then you construct its k particle density matrix, that's this object here, and then you sum over all n by putting this weight e to the minus beta kappa n. A little bit like a Laplace transform in n, if you like. And you divide, there's a normalization. I'm not going to comment why we choose this, but that's the usual and natural way in the grand canonical setting. Okay, and the theorem, without surprise, is the following. So in one dimension, we assume that V behaves like x to the s with s bigger than 2. Then we know the mass is well defined, everything is fine. And then the theorem says that lambda to the power k times gamma k converges to what we want, namely u tensor k times our nonlinear Gibbs measure, and this for all k. I have to make some comments about the limit. So before we had n to infinity and lambda to 0, and lambda was 1 over n, but now there's no n anymore because we've averaged over n. So here we can only take lambda to 0, but we need another parameter, and the other parameter is beta, the inverse temperature, and it turns out that the right limit is to take beta of order lambda. So beta goes to 0, and this means that it's a kind of high temperature limit. So we have to put a lot of randomness in our system in order to see these nonlinear Gibbs measures arising. So this was actually the first result about the derivation of nonlinear Gibbs measures from quantum mechanics. And then there were several improvements and extensions. In particular, there are very nice works by Fröhlich, Knowles, Schlein, and Sohingers. They also managed to treat the time-dependent case in 1D. So let me now turn to the difficult theorem. So the one I mentioned that we published in Inventiones last year, which is about the renormalized problem. So it's a bit the same theorem. So we work in dimensions 2 and 3. We assume that V behaves like x to the s as before. We assume that s is large enough. And then the theorem says that lambda to the k, gamma k converges to the same thing with a renormalized dense Gibbs measure. And the limit is the same, that lambda goes to 0 and beta behaves like lambda. So one big difference, of course, we have to do something at the level of the quantum problem. And one big difference is that we have to now move the parameter kappa. And kappa has to depend on lambda in this explicit way, which is written here. Okay, so it has to be the fixed kappa that we want, and then minus a correction which actually diverges. Okay, so kappa lambda now diverges to minus infinity, and you see it diverges in a universal way, okay, a way which depends on kappa in an explicit way and depends on W in an explicit way. Actually, of course, if W is 0, then there should be no renormalization, so it's clear that it has to depend on W, but otherwise it only depends on the integral of W, and otherwise you get this universal factor here in front. Okay, so we use the chemical potential, if you like, this parameter kappa, in order to naturally obtain a renormalization in the limit for this nonlinear Gibbs measure. However, there is a little surprise, which is that we do not get the Gibbs measure associated with the fixed kappa and the fixed V that we started with. We get a measure with a slightly modified V, which I call V0 here. Okay, So we will get the Wick renormalized interaction I here, and then the mu0 will be the Gaussian measure of covariance minus Laplace plus V0 plus kappa minus 1. And V0 is itself a solution of a nonlinear equation, which is not so nice, which I wrote here. Okay, so by playing with this parameter kappa, we are able to renormalize the problem. We get a renormalized nonlinear Gibbs measure in the end. However, it has to be written in a way that everything makes sense. And the way to write it is in terms, is in terms of this potential V0. And why do you need this V0? That's because you see, you want the new energy, so the energy with V0 and the renormalized interaction to be related to the old energy. And if you do a formal computation, everything is going to be explained in the proceedings, then you can see that this exactly coincides with energy plus mass times kappa minus alpha plus beta, where alpha and beta are infinite parameters which are doing the renormalization. Okay, so this theorem has been proved simultaneously by Fröhlich, Nonlinear, and Schrödinger with a completely different method. We actually use a variational method in order to prove this theorem, and they use some completely different tools. But perhaps I would like to insist, I would like to insist on the fact that in mathematics, it's often forgotten that renormalization, you should be able to renormalize the problem by only playing with the physical parameters of your problem. You should not do something crazy. You should not just cross out the bad terms that you don't like. You have to be able to show that you can renormalize by playing with only the physical parameters of your system. And that's exactly what we are doing here with the parameter kappa. So now is the last slide. I'm coming close to the end of my talk. So maybe 2 words about the strategy for proving this theorem. So as I said, we actually use a variational characterization, both from the renormalized Gibbs measure and the quantum state. And you have to think that we are doing some kind of gamma convergence. So we have a minimizing problem at the quantum level, and we want to show it converges to the minimizing problem for the measures. And then what we do, we first reduce to finite dimension using the strong solidity of entropy, which was mentioned on Wednesday by Rupert Frank in his Laudatio for Lib. It's one of the most famous results of Lib. And once we've done that, we apply quantum definity in finite dimension with quantitative errors. But the real difficulty is to control the interaction, because of course, the interaction is divergent. It contains divergent terms which compensate each other, and we have to show that everything gets renormalized in the right way. And for this, we had to invent some new quantum correlation inequalities, but it would lead us way too far to explain this in detail. So you can have a look at the paper if you are interested. Conclusion. So I hope I've explained that this quantum definity point of view provides a new and somehow more conceptual interpretation of Bose-Einstein condensation, or more generally, the validity of the mean field for quantum systems. It's always good when mathematics can bring some new insight in physics and not just rigorously prove what physicists know. And I think it's really one case where we can really actually bring some new interpretation. So this allowed us to prove some new results for Bose cases when we married this quantum definity with techniques from the calculus of variations and PDE. And they are big open problems. For instance, one is to understand Gibbs measures in the dilute regime. And another one, which is even bigger, is to go outside of the mean field and dilute regimes. But that's not for today, that's for the next time. So thank you very much for your attention. I will now connect on Discord in case there are questions. Please go there if you have a question. Don't hesitate to ask. Or you can also just send me an email. It's easier. Anyway, thank you very much.
Thank you very much for this very nice and clear talk. I think we're just perfectly in time. Also like to thank the audience for coming, and we'll see you, hope to see you in the later parts too. So have a nice rest of the day. Goodbye.
Bye-bye.
Thank you very much, guys. So I had to wait